Most people walk past them without a second thought. Rough, broken, stained with rust, buried beneath dirt and gravel, these rocks appear completely worthless. But hidden inside some of them is something that has fascinated humanity for thousands of years. Gold. Not the bright nuggets you see in movies or treasure hunts, but microscopic veins and fragments locked deep inside ordinary stone. Nature rarely reveals its treasures openly. Instead, it hides them beneath layers of rock, pressure, heat, and time. And the incredible part is this: with enough patience and understanding, you can sometimes uncover that hidden gold using nothing more than natural forces. Everything begins with observation. When searching for gold-bearing rocks, appearance can be deceiving. The rocks that hold value are often the ugliest ones in the landscape. They may look burned, cracked, heavy, or stained with reddish-brown marks caused by iron oxidation. To most people, they seem lifeless. But to an experienced eye, those colors tell a different story. Gold is commonly associated with hydrothermal systems, places where hot, mineral-rich fluids once moved through cracks deep underground. As those fluids cooled over millions of years, minerals began to crystallize inside the fractures. Quartz formed, sulfides formed, iron minerals formed, and sometimes gold formed alongside them. That is why rocks containing quartz veins, rusty streaks, black mineral patches, or metallic flecks deserve attention. Even tiny sparkling grains that resemble fool's gold can be important clues. Minerals like pyrite and arsenopyrite often appear near real gold deposits. They are nature's fingerprints, signs that mineralization once occurred in that area. The earth leaves evidence everywhere. Most people simply don't know how to read it. Once suitable rocks are collected, the next step is one of the oldest techniques ever used in gold recovery: fire. Long before industrial machinery existed, people discovered that heat could weaken rock and expose what was hidden inside. It wasn't advanced technology. It was observation, experimentation, and patience passed down through generations. When intense heat is applied to rock, every mineral inside reacts differently. Some expand faster than others. Quartz expands differently from iron minerals. Sulfides respond differently from surrounding stone. Under enough heat, the internal structure begins to stress itself apart. Tiny fractures begin forming deep inside the rock. At first, nothing seems to happen. The stone simply darkens as flames surround it. But slowly, invisible pressure builds within. The bonds that held the rock together for millions of years begin weakening. The stone starts losing its strength from the inside out. This process is not about melting gold. Gold survives extreme temperatures far better than many surrounding minerals. The real purpose of heat is to loosen the prison trapping it. Even a controlled wood or charcoal fire can create enough thermal stress to affect certain rocks. The key is slow heating. Too much heat too quickly can shatter material violently and destroy valuable pieces before they can be examined properly. Patience matters. As the fire continues, surfaces begin to change color. Cracks become visible. Some rocks develop dull gray patches, while others split along natural fracture lines. It is almost as if the stone is slowly surrendering its secrets. Then comes the second force of nature: water. The moment heated rock touches cold water, an entirely new reaction begins. Rapid cooling creates thermal shock, one of the most powerful natural fracturing processes found in geology. You can often hear it immediately. Sharp cracking sounds echo as water rushes into microscopic fractures created by heat. Steam escapes. Layers begin separating. Weak points expand. What looked solid moments earlier suddenly becomes fragile. This transformation is powerful because rock cannot contract evenly after extreme heating. Different minerals shrink at different speeds, forcing the stone apart from within. Nature itself becomes the tool. When the rocks cool completely, the difference becomes obvious. Some break cleanly into sections, others crumble under pressure. Veins hidden deep inside become exposed for the first time. And this is where careful observation becomes critical. Inside fractured rock, you may begin seeing metallic streaks, dull yellow patches, quartz-lined cracks, or tiny glimmers trapped between mineral layers. Not every sparkle is gold, of course. Pyrite can deceive beginners very easily, but real gold behaves differently. It doesn't tarnish. It doesn't lose color when rubbed. And unlike brittle minerals, gold bends rather than shatters. Sometimes it appears only as tiny specks barely visible in sunlight. Other times it forms thin threads running through quartz veins like frozen lightning trapped inside stone. Crushing the material further helps separate these hidden particles, but the process must be controlled. Pulverizing everything into fine dust too quickly can make recovery harder. Gradual crushing allows valuable material to be identified before it disappears into powder. Each crack reveals more of the rock's hidden story. Every fragment broken apart exposes minerals formed millions of years ago beneath unimaginable heat and pressure deep inside the Earth's crust. What you are witnessing is not just extraction, it is geology unfolding in your hands. But even after crushing, the final challenge still remains: separation. Fortunately, nature already provides a solution. Gold is extremely dense, much heavier than most surrounding minerals. That weight becomes its greatest weakness and your greatest advantage. Place crushed material into water and begin gently swirling it. Lighter particles such as sand, clay, and crushed stone move easily with the current, but heavy materials resist movement. They settle stubbornly at the bottom. This simple principle has been used for thousands of years. Ancient civilizations recovered gold long before modern chemistry existed because gravity itself does most of the work. The process requires calm, controlled movement. Rush it, and valuable particles may wash away unnoticed. But with patience, the lighter debris slowly disappears while heavier concentrates remain behind. And then, sometimes you finally see it. A small golden flash beneath dark sand, a stubborn metallic flake that refuses to move, a glimmer that catches sunlight differently from every surrounding mineral. At that moment, an ordinary rock becomes something extraordinary. What once appeared worthless reveals itself as part of one of nature's oldest hidden systems. Fire weakened it, water fractured it, gravity separated it, and patience uncovered it. That is the remarkable part about gold in nature. It rarely announces itself openly. It hides behind layers of stone, disguise, and time. Only those willing to look closer ever notice the clues. Most people see rocks. Others see stories written across the earth itself. Every stain, crack, mineral vein, and shimmer carries evidence of ancient geological forces still shaping the planet today. Understanding those signs changes the way you see the world forever, because the greatest discoveries are rarely lying in plain sight. In the quietest corners of American wilderness, far from paved roads and phone signals, there exists a geological pattern so consistent that geologists almost treat it as a coded message from the earth itself. A message written in stone, whispered through time, and understood only by those who know how to read the land. They call it the three-rock combination, a natural lineup of minerals and textures so tightly connected to gold that whenever these three appear together, the likelihood of gold rises from possibility to near certainty. Most people walk through valleys and stream beds without noticing the clues lying at their feet. But gold is never random. It never scatters without logic, and it never travels alone. It forms, moves, and settles according to precise geological laws. Laws that leave unmistakable signatures behind. These signatures aren't obvious. They don't shine, they don't sparkle, and they don't call attention to themselves. But geologists have learned to recognize them as the silent fingerprints of ancient gold movement. And today, you will learn to recognize them too. Gold begins deep underground, born from mineral-rich fluids rising from molten rock far beneath the crust. As pressure builds and temperatures soar, microscopic particles of gold dissolve into superheated water, drifting upward through cracks, fractures, and faults. And as the planet cools those fluids, gold begins to precipitate out, sticking to the edges of the fractures, coating quartz veins, pooling inside breaks in the bedrock. This entire process leaves behind companions, rocks and minerals that form under the exact same conditions. When you understand these companions, you understand the entire Golden Trail. The first of these geological companions is a type of metamorphic rock that looks as though it has been pressed, heated, and folded by the weight of the continents themselves. Smooth, shiny, layered, and often glittering with mica, this rock records ancient heat and pressure stronger than nearly anything on the surface today. Geologists rely on it because this type of rock forms in the exact environment where gold-bearing fluids originate. It is schist, one of the most respected host rocks in American gold geology. Whenever you step into a region where schist appears, especially in mountain belts stretching from the Appalachians to the Rockies, you stand inside a zone shaped by the very same forces that produce gold. But schist alone isn't the signal. Gold needs a highway, something that carried the fluids upward and froze them in place. And for millions of years, that highway has been quartz. Thick white or translucent quartz veins cut through darker rock like frozen lightning. They slice across schist, granite, basalt, and almost anything in their path. When hydrothermal fluids carrying gold cooled inside these veins, they left behind crystals, fractures, iron staining, and sometimes visible flakes of precious metal frozen in time. Even the rusty orange-red stains that coat quartz in gold country tell a story. They signal iron oxidation, nature's way of marking the path of mineralization. Where quartz cuts through schist, the story of gold becomes clearer. But the real confirmation appears in a third rock, an often overlooked heavy, rusty, metallic stone that forms at the surface when iron-rich minerals weather. It can appear deep brown, jet black, or blood red, and it leaves stains on anything it touches. This stone is ironstone, the unmistakable marker of a hydrothermal system that once pulsed with mineral-rich fluids. Gossan caps, iron crusts, limonite masses, and hematite-laced stones are nature's final stamp of approval. They say, yes, the chemistry, the temperature, and the fluids that create gold were here. When schist provides the birthplace, quartz provides the pathway, and ironstone reveals the chemical transformation. The three-rock combination is complete, not a myth, not a rumor. A geological pattern repeated across the United States wherever gold has been historically and scientifically confirmed. From the Sierra Nevada range to the Georgia Gold Belt, from Arizona's iron-rich ridges to Colorado's metamorphic cores, from the river-cut canyons of Oregon to the ancient schist belts of Alaska, this trio appears with remarkable consistency. Finding these three rocks is like reading a coded map. First, you notice the schist, layered, glittery, easily split, shaped by immense heat. You run your hand across its surface and feel the grain of an ancient world. Then you notice the quartz, bright white, jagged, cutting across a darker rock like veins of frozen sunlight. And finally the ironstone, heavy, metallic, oxidized, a deep, rusty color that stands out even in the shade. These rocks are not random. Their presence together is a geological conversation, and each stone adds a layer of meaning. Gold hunters, prospectors, and professional geologists use this combination in the field without fanfare. They know that if schist and quartz appear together, the ground has history. But when ironstone joins the scene, the ground has potential. And And when all three appear within walking distance, sometimes even within arm's reach, you have stepped into a zone where gold once moved, gathered, and concentrated. This is the exact method used in American exploration. Locating metamorphic host rocks, tracing the quartz veins that fracture them, and studying the oxidized ironstone that reveals the age of the system. Companies invest millions in drilling programs based on this geological triangle. Prospectors stake claims on ridges where these rocks intersect. And ordinary people, those who understand these quiet clues, find gold in places others overlook. When you walk into a landscape with these three rocks, you begin to see the world differently. Hills that once looked ordinary now appear as chapters in an ancient story. River bends become pathways that once carried broken quartz downhill. Rust-colored ridges become signposts pointing toward old veins. Even the gravel beneath your feet becomes a record of erosion, carrying fragments of the very rocks connected to gold. The power of the three rock combination is not just scientific, it is practical. It tells you where to look, how to interpret the land, and where gold is most likely to be trapped today. It teaches you that gold does not scatter randomly, but follows rock types, structures, and chemistry. And once you understand those patterns, you can predict where gold should be, even in places you've never explored before. Whenever you find yourself in a canyon, along a creek, or on a lonely mountainside in the American West or East, and you notice these rocks around you, schist whispering of deep origins, quartz marking the pathways of ancient fluids, and ironstone confirming the mineralizing conditions, stop for a moment. Look around. Listen to the silence, because you may be standing on the threshold of an area where nature once hid gold with deliberate precision. And the landscape around you is quietly waiting for someone observant enough to interpret it. The truth is that gold rarely reveals itself easily, but it leaves unmistakable hints in the rocks that accompany it. When you know how to read these hints, the wilderness becomes a geological map rather than a mystery. And this second part of the story begins with understanding what happens next, how to follow these rocks, how to interpret their placement, and how to transform geological clues into real discovery. Once you identify schist, quartz, and ironstone in the same environment, the next step is to determine how these rocks relate to each other. Geologists are trained to look for alignment, orientation, and the way veins intersect the host rock. When quartz veins cut across schist in clean, sharp lines, it means those veins likely formed during a period of intense hydrothermal activity. And hydrothermal activity is the engine of gold formation. These veins can run uphill, downhill, or across a slope, but they usually align with old fault structures, cracks in the earth that once served as pathways for mineral-rich fluids. By following the direction of the vein, you essentially trace the path that gold-bearing fluids once traveled. Ironstone plays an even more important role at this stage. Its presence does not just confirm mineralization, it reveals the age and exposure of the system. Ironstone typically forms when sulfide minerals weather and oxidize at the surface, which means the area you're standing in has undergone long periods of erosion. When these oxidized caps sit above quartz veins, they often point toward deeper, unweathered sections where gold can remain locked inside the rock. This is why some of America's richest gold finds have been made just beneath iron-rich hilltops. The rusty color is not just a stain, it is a sign of ancient chemical transformation. As you walk along slopes or creek beds in the United States, you may notice that these rocks appear in clusters. This clustering is not accidental. Water, gravity, and erosion naturally concentrate the fragments of these rocks together, especially near old volcanic belts and metamorphic terrains. When all three appear in creek gravels, it often means the original source is nearby, uphill or upstream. This is one of the most important clues prospectors use. Rocks always travel downhill, and gold, being heavier than nearly everything around it, tends to settle in predictable traps. So if you find these rocks together in a waterway, the next step is to trace their origin. Tracing uphill from a creek, following the fragments of schist and quartz, often leads you to the bedrock exposures where the original veins remain frozen in place. Along the way, ironstones scattered across slopes confirms that the ground has undergone oxidation and mineralization. Every rusty fragment you touch is part of a chain of evidence stretching back millions of years. And as the rocks become larger, more angular, and more freshly broken, you know you're getting closer to the source. American geologists often refer to this approach as reading the land, because the terrain itself is the text. The shape of the valley, the tilt of the hillside, the position of old boulder fields, all carry meaning. Gold-bearing areas frequently appear where steep slopes flatten, where ridges intersect like braided threads, or where old river channels changed direction long ago. If the three-rock combination appears in these zones, the probability of gold increases dramatically. Many of the best modern gold discoveries in the United States weren't found by accident. They were found by people who understood how to interpret rock combinations and follow them back to their origins. And it is here where the process becomes almost meditative. You take your time, you slow your steps. You observe the ground with calm curiosity. The wilderness becomes a quiet teacher. Small details begin to stand out. The sound of crunching iron-rich gravel under your boots. The distinct shimmer of mica from schist in the afternoon sun. The glint of white quartz between broken stones. You begin to sense a pattern. The environment feels mineralized, as if the land itself still remembers the ancient pressure, heat, and geological violence that once shaped it. When you reach the source area, whether it's a ridge, a hillside, or a bedrock exposure, you'll often notice the rocks aligning in a way that tells a story. Quartz veins may widen, ironstone patches may intensify, and schist layers may twist and fold in dramatic patterns. Sometimes you find broken quartz scattered downhill from a vein exposed high above. Other times you see rusty staining on the face of a rock wall, indicating that sulfide minerals once lurked inside. If you examine these surfaces closely, you may notice tiny fractures where gold once moved. Even if the gold is not visible, the structure of the rock carries the memory of mineralizing fluids. And this brings us to one of the most powerful techniques geologists use: examining contact zones. A contact zone is where two different rock types meet, such as the boundary between schist and quartz. These boundaries are prime locations for gold deposition because the change in chemistry and pressure often cause gold to drop out of solution. When quartz veins cut through schist and ironstone coats the edges of those veins, the chances of gold increase significantly. Many American gold mines began at these exact boundaries, but gold is rarely found at the surface. It is usually locked inside the quartz veins, trapped in fissures, resting in cracks in the bedrock, or broken off and carried into nearby waterways. This is why panning in areas with the three-rock combination is so effective. If gold has eroded from the veins, it will settle into natural traps, behind large stones, inside cracks in the bedrock, beneath dense gravel layers, and in places where fast water suddenly slows down. These traps exist everywhere from Alaskan streams to Appalachian rivers, And because gold is so heavy, once it settles, it tends to stay put until major floods move it again.